Okay, so welcome back. We're going to go through a few practical examples on how to evaluate the profile of a compound subset and also how to select one in the first place. And then we will move on to the last section of this MedChrm Studio tutorial dealing with matched molecular pair analysis. So let's restart where we left off, and so we're going to read this set of 2600 compounds that we just exported, which were our exploded products from class 1. So we can read these compounds in now, and I'd like to draw your attention to the fact that the compounds that were part of the 299 exemplified subset have an identifier starting with EDX in the product in class column, whereas the compounds that have remained virtual and were not exemplified do not have any entry in this column. And that's going to become important for some of the analysis work that we're going to perform next. So the first thing we're going to do is to calculate ADMET properties for these compounds. So let's just go ahead and calculate properties like we've done before. Again, ADMET Predictor is very fast. This is a multi-threaded calculation. I'm running on a standard laptop here, and I've set it to run on 7 threads. So again, it proceeds really quickly. And well, here we go. We're already done. So the results are back. So one of the things I'd like to show you is the distribution of properties for the exemplified subset. And these are compounds that were actually made. So if we take a property, for example, like solubility or predicted solubility in this case, we have to look for S plus SW. So let's go ahead and look for our native solubility model. And we're going to actually use a log space here to do our display. So this is the distribution for the entire set of 2600 compounds. Now, if we want to see just the compounds that were exemplified, the 299 that were exemplified, we can simply use the search function. So this is found under Edit, Find Text, or Control F as a keyboard shortcut like you would do in Word or Excel. Just do Control F and search this product in class column. So this is the search attribute, would be product in class. You can really search for anything, but we're only searching this column for EDX. And just go ahead and do this. And that will select all of the compounds that have an EDX, well, an identifier entry in the product in class column. And then select the update chart, okay, at the top of, in the header of chart 1. And this will give you the overlay of the distributions between the selected compounds, that's the exemplified set, and the compounds that remain virtual. And what you can see is that there is a rather strong bias in the exemplified subset for compounds that have higher solubility or higher predicted solubility in this case, which is exactly what you want. Also notice that you have two different axes, two different y-axes in this particular chart. On the right, this is the scale for the selected compounds, the 299, and on the left-hand side, the other y-axis is for the unselected compounds. And you can do this kind of plot for any of the properties. Say, for example, you want to see a similar distribution, say for ADMET risk, simply go and select ADMET risk as your property. In this case, you would unselect the log scale and display this. And again, you see that the subset that was selected for exemplification is significantly biased towards compounds that have a lower predicted ADMET risk. So as you can see, there's a lot of work that has gone into the design of this subset. And what I'd like to show you next is how you would go about selecting a subset of your own. So this is pretty easily done. The first thing we have to do is actually go to chemistry and go back to what we've used before, which is our generate classes option. Okay. And what we've done before is really clustering, but now we know we're dealing with a single cluster. All of these compounds really came from our previous class 1. So all of these compounds are really a single cluster. So in this particular case, we're going to select single superclass as our option to generate classes. Okay. And you will soon see why we're doing this. And now if we go to classes, of course, we only have one class. And at this point, you need to define what's going to be used as the scaffold in order to divide the compounds, or to analyze the compounds in terms of core and R group representation. And the way you do this now is with your right mouse click, go to scaffolds, and you can define your scaffold using maximum common substructure. So go ahead and do this. You can leave the defaults the way they are and select this. And now this is our scaffold. So I'd like to draw your attention to something a little bit more advanced, that if you're dealing, say you have a scaffold and you have an ethyl group and say a propyl group, and if you use this MCS approach, maximum common substructure approach, to identify your core, it will probably identify the extended scaffold with the ethyl group as the core, and then just have a hydrogen and methyl substituent instead of the ethyl propyl, which is the way that you really want it done. So if you get into that kind of situation, you can actually edit the score by hand. So similarly, under scaffold, you can refine or modify the definition of your core using a lasso technique. So for example, here, if we decided that instead of this entire set of compounds being the core, we actually only want this to be the core. So you could do this as well. So again, you can do some manual touch-up on the way that the scaffold was identified. So we're just going to cancel here and leave it the way that it is. So at this point, we can go to our R tables because we've defined our core, and the software will again give you the breakdown of our 2,600 molecules in terms of core and R group. And at this point, you can actually proceed to the selection of a subset. So in order to do so, under R tables, you will find this option, Find Subset Using R Groups. So you can select this. Under Find Best Subsets, you can define which property you want to use to define your subset. So maybe you want to optimize against solubility or against ADMET risk, which actually contains multiple properties. So for example, if we want to use ADMET risk, we will use minimum number of unconstrained R positions as 1, maximum number as 3, we have a total of 4, and the number of compounds in each subset, in this case 100 is pretty good. And this is the number of solutions that the software will output, the maximum number of subsets to identify, maximum number of solutions. Notice that for ADMET risk, the lower value is desired. So we're going to leave this larger attribute values or better option unchecked. If you were dealing with something like solubility, you would actually want a higher value, so you would turn this on. Okay. So we're going to use this and say OK. And the software will actually identify, it will show you the R group combination that results in the optimized subset, and you can directly see on chart 1 here the distribution of ADMET risk compared to the unselected compounds. So we have 100 compounds, which was the target number to select, and 2,500 compounds that are unselected out of the 2,600. And you can see there's a very strong bias towards compounds with low ADMET risk in our subset compared to what remains unselected. Okay, and using this arrow here, you can basically advance towards the multiple solutions that were output as part of this selection process, and notice that our graphs are updated in real time to show you what the distribution of properties looks like. Okay, so that concludes that part of this library design work. We're going to switch gears now, and I would like to show you a few things about matched molecular pair analysis, which is also known as activity or property cliff detection. And I say activity or property because usually this kind of analysis is performed on activity, and again, it's often called activity cliff detection. However, this is something that you can do on any property that you can import or calculate within the software. So in order to do this, we're going to load a different subset. We're going to load this set of enamine compounds from their discovery set. Okay. And as we've seen before, the first step in performing this kind of work is to calculate properties. So we're going to do this, calculate ADMET properties, and just go ahead and calculate. And we have 2,000 compounds here, so it's going to proceed rather quickly. And we don't have activity data here, so we're just going to use properties for the sake of the exercise. And what we're going to investigate is what chemical changes result in the most dramatic changes in that predicted property that we select. So the first step is under chemistry. Here you will find the option to generate pairs. Okay, and there are a number of options, but the most important one is on which property do you want to do this. So for example, you could select an activity column, or in this case we're just going to use our native solubility. Okay, so if you're happy with your parameters, just click OK. And this calculation is also multi-threaded. So we're using our 7 threads, so it's going to proceed really quickly. And the results are going to be found in our pairs tab over here. So if you select this, you will see which changes in chemistry, relatively small changes, result in potentially large changes in the target property that you are investigating. So here you're going from a thiolane to a pyrrolidine, and you can see the somewhat dramatic change in solubility from turning one into the other. Likewise, going from a thiophene to a furan here, we also have a pretty significant change, or from a cyclobutane to a methyl ether, we also have a pretty significant change. And of course, you can sort these changes by magnitude. So by simply clicking on the top here, you can sort them from small to large or large to small, which is what we have now. So again, the software provides you with a very easy way to investigate how dramatic certain changes, again, in activity or property can be depending on relatively small chemical changes. So again, I hope this was useful. It concludes this tutorial. Thank you for your time and have a wonderful day.